Thanks so much for joining us today. Really looking forward to this presentation and hearing about some climate change monitoring and research projects that have been ongoing in the Skeena region in Northwest BC. Really thrilled that Vanessa has been able to join us again to share her knowledge. I'd like to acknowledge that I'm hosting today from the traditional territory of the Gitumden clan of the Wet'suwet'en Nation, and grateful for our presence on their land and the beautiful space that we live and learn in. I would also like to thank Bulkley Valley Community Foundation and Bulkley Valley Credit Union for their support of the seminar series and has enabled the center to purchase video conference room equipment as well as seminar hybrid equipment. It's been great to be able to expand our reach that way. Many of you know Vanessa from her previous presentations, so I will skip the introduction and let her just launch right in, and then we'll have lots of time for learning and question and answer afterwards. So welcome again, Vanessa. Thanks so much and great to have you.
Thank you so much for having me. I really appreciate you having me back. And I do apologize. Don and I had planned that this would be in person. I had hoped to be out in the fields, downloading the installations that I'm going to talk about today. But yeah, if you're a Ministry of Forest researcher yourself or have colleagues that are researchers, you probably know that we're in a weird year where we don't have any funding. So I'm scrambling to look for volunteers to come out with me. And if any of you are interested after seeing this presentation to get out to some of these sites, please do let me know. So yeah, I was here in early February talking about climate change trends. Again, if you are a ministry researcher or work with researchers, you know that only 50% of our job is doing that kind of communication, outreach, consulting, more operational type work, and the other 50% we are able to run field programs. So that's mostly what I'm going to talk about today. And this picture here on my introductory slide is one of the weather stations that was installed in collaboration with the Tultan Land Guardians up around the alpine areas of Dease Lake. And we got that installed a couple summers ago. Hopefully my slides changed. Please interrupt me if they didn't. I did embarrassingly give a presentation last week where I was advancing the slides on the wrong screen, and you know, that's always not fun, but it does happen. Just an overview of my network, and if you don't know me, I am the research climatologist for the North area of the Ministry of Forests. This is actually my 20th year in that position, which is pretty exciting. And since the start of that position, I've been really building a monitoring network to answer some of our questions around how is climate changing in northern British Columbia and how it's impacting our forest and ecosystems. So the result of that to date is about 40 weather stations across northern British Columbia and available on this little shiny app. The link is down below. 10 of those have been installed in collaborations with other groups like the Land Guardians that was showed on the title slide. I have kind of a mixture of different equipment depending on what I can either afford or what might be gifted to me from folks that have retired. So 3 of those are Campbell Scientific based equipment, which I inherited from Dave Spittlehouse, which I know some of you would have known. He was our provincial climatologist previously. And he actually still helps out with those stations, which is amazing. 2 are Davis weather stations, which some folks might be familiar with. They're more of an agriculture or backyard weather station. And then the remainder of the equipment I run is onset equipment. So with those 40 weather stations and actually 365 approximately additional data loggers looking at microclimate, not just weather, I do have about 1,056 sensors or measurements, which equates to over 25,000 data points per day and over 9 million data points per year. And all of that data is looked at pretty heavily by both myself and a research tech. And then for the weather stations, we clean that data up as much as possible and post them on this site here. For 2024, that equated to 171 field visits. So definitely I am panicking without any research funding or tech support this year because I have to make the most of the field season. So on this app, there's actually 43 weather stations if you were counting them all for fun. 3 of those are run by our research hydrologist, Alex Bevington. So my research weather station network is part of a ministry research network called the Forest Ecosystem Research Network. The province of British Columbia also runs a climate-related monitoring program. This is led by the Ministry of Environment, and researchers like myself running weather stations for their own research questions do share the locations of those stations as well as some of the data through the climate-related monitoring program in an effort to improve monitoring across the province. For myself, I share 37 of those stations annually, also to the Pacific Climate Impact Consortium weather station data portal. And the green dots in that PCDS graph are all of the fern weather stations that are shared by myself and others. So you can filter directly for this research ecosystem network on that P.Ag site if you were interested. We do actually contribute a significant amount of observations to provincial monitoring, which is kind of cool. This slide I've taken from Francis Sweers, who is with the Pacific Climate Impact Consortium. This is from his report to that BC Climate-Related Monitoring Program Annual Administrators Meeting for 2023. So I don't have stats up to 2024, but this is how our network was contributing in 2023. So between all the researchers sharing data, we submitted over 9 million observations just for 2023 alone. And it looks like we make up about 20% of the province's climate data per year. So support for fern, and specifically, I call it Fern North VF. So that's just the northern stations that I run. I have to acknowledge my research tech, which has been working with me about 50 to 75% of the time for the last 9 years, is Rebecca Bowler. She has her master's from UNBC and is also a professional agrologist. And then Alex Bevington, our research hydrologist. We kind of have installations in some of the same locations. I think Alex is actually headed to the Northeast today and might be downloading one of my weather stations, so we kind of share logistics. The Ministry of Forest Health Program, I've been collaborating with quite a bit lately to install more weather stations, which is fantastic. The Ministry of Environment has been supporting my network for the last several years with capital items because researchers are challenged by not being able to buy equipment above $1,000. So Ministry of Environment helps me with that. Numerous students and volunteers, Indigenous land guardian programs, the College of New Caledonia. We actually have an additional 10 forest climate research stations that I haven't included in this, but we are doing similar efforts to improve forest climate monitoring around the Prince George area through the College of New Caledonia. And most of this is funded through the Ministry of Forest Research Program at about $90,000 a year, which sounds like a lot, but most of it is going to that research tech. Only about $40,000 is operational costs, and 20 of that is just travel and equipment and hardware, tools, all those kind of logistical things. So to run 40 weather stations on about $20,000 is actually quite a bargain. So here's what the app looks like. If you are interested in any of these stations, the data is all available. It is just daily data. If you need the hourly data, you'd have to contact me directly for that. But please, if you're interested, feel free to grab data and use it for whatever purposes you like. Some of the weather stations do go back to 2007, so we're getting some pretty long records. What's nice about these apps is there's pretty cool data visualizations and interactive graphs. If you've ever played with these shiny apps before, where you are able to zoom right into a particular year or month and get more information. So you can get a lot of information from the site directly without even downloading the data. There's a climate summaries tab called the statistics tab, where you can go in and filter for a station. You can pick different summaries such as annual, monthly, seasonal, or growing season, and then look at all the different climate variables that that station has, and you can export that data directly. If, for example, you were curious about April temperatures in 2022 for something near maybe one of your field sites or just out of interest. There's also a real-time data tab. Only 10 of my weather stations are currently communicating in real time via satellite and the Iridium network, and is hosted by Data Garrison. And the reason it's only 10 is it is quite expensive. It's about $1,000 per year for me to do that. And yeah, that comes out of my research budget. 7 of those 10 stations are in the alpine. I know the Smithers community is pretty curious about what's going on in the alpine, and there is one on Hudson Bay Mountain, which some of you may already be familiar with. So that data you can either get from this Shiny app or from the Data Garrison link directly. And I wasn't able to put together too many slides on what I've learned from alpine monitoring so far, but just have like a few little learnings on the corner there. And most of you probably already know this too, that it's really windy, but I didn't realize quite how windy it can quite often be above 160 kilometers an hour, which is well above hurricane force. Minimum temperatures in the alpines are relatively warm. And that has led us to do some work on temperature lapse rates in these alpine areas, where we're taking the temperature differences between stations at lower elevations compared to these alpine sites and calculating monthly lapse rates. And what's interesting is there's a big geographic difference. So we've seen that our most southerly station around Valemont and Canoe, lapse rates are around 5 to 6 degrees per kilometer, which is pretty close to the wet adiabatic lapse rate, so that makes sense. But then up around Toad River, Mencho Lake Park in the Northern Rockies, lapse rates are closer to about 0 to 1. So a huge difference, and that really is important for improving our climate models as adjustments in lapse rates based on these high elevation data sets are still something that is being worked on. So the purpose of my network, it is for forest climate research to understand the climate and impacts of climate change to northern BC forests and ecosystems. I run 5 projects with installations. So one is climate change indicators in northern ecosystems. There's really 4 sub-projects with that one around lodgepole pine rusts, which I'll talk more about today, tree improvement, alpine, and this was work that was initiated by Will Mackenzie, and I've since taken over some of his sites in the north and tried to keep them going. And also biogeoclimatic ecosystem classification variant monitoring gaps. So we're trying to put in installations to gather climate data in variants that previously had no climate data. Another project I have is climate change and permafrost, and this is in mountain and isolated patches, mostly in the Northeast region. A project on mountain pine beetle carbon and water flex, which is a FlexNet tower that's run out of UBC, but the Ministry of Forests is the current sole supporter. Kiskatinaw Climate Change, which is a collaboration with the city of Dawson Creek, as they're quite concerned about their water supply, primarily around drought and the impacts of mountain pine beetle to their area. And then finally, wildfire risk of different stand types, microclimate and soil effects. That's great that Dawn mentioned. Larry and Phil will be talking more about that in coming weeks. So I'll just talk about the microclimate side of that project so far. The second purpose of the network is really to improve climate monitoring in northern British Columbia, to fill provincial monitoring gaps, mostly in underrepresented areas such as mid to high elevation and in forests, and unrepresented climate variables like pressure, solar radiation, leaf wetness, soil moisture, and soil temperature, which are hard to find in some of the other provincial networks. And then to contribute to climate model validation, review, and potentially climate model improvements. So the rest of the presentation, I'm going to talk about two projects that do have installations in the Skeena region. The first one is on lodgepole pine stem rusts and climate. So this work is done in collaboration with Rebecca Bowler, Jewel Yurkowicz. It was initiated by Richard Reish, who was with the Ministry of Forests and then moved on to the College of New Caledonia and has since retired, but is one of those working retirees. And then our current regional research pathologist, Kelly, here in the Dominica. And then shout out to Alex Woods, who I'm sure lots of you know. He has been an advisor on this project from the start, really helping me figure out what climate variables are important for lodgepole pine stem rusts. So there's several study locations. For this presentation, I'm really only going to focus on Endako, Thompson, and George Lake. But there are other locations around the central interior. The Endako, Thompson, and George Lake sites are part of a Commandra screening trial, which was planted in 2004, and the climate monitoring began in 2007. The Crystal Mackenzie Junction progeny trial, which was planted in 2009, 2010, and 2012, with climate monitoring in 2010. Prince George Tree Improvement Station, which is a ministry seed orchard, the lodgepole pine stands that weren't impacted by the mountain pine beetle now decades ago, the ones that survived. We've been doing climate and disease monitoring in there since 2007. There's a graph trial around East Boulder Creek that was established in 2010, and climate monitoring also in 2010. And then lastly, the Chief Lake Commandra Resistant Screening Trial, second cycle, which was planted in 2002 and climate monitoring in 2019. So as a climatologist, certainly rusts and diseases of lodgepole pine is not my area of expertise. So I'm just going to be talking mostly about the climate work that has gone into these programs. But here's a little bit of background information on this Commandra screening trial. So it was initiated by the Ministry of Forests, West Fraser, Isabella Point Forestry, Burns Lake Community Forest, and Babine Forest Products. And it's 1.5 meters by 1.5 meter spacing of interior lodgepole pine from 130 seed lots, 7,440 trees on each of those 3 sites. So forest health assessments have been done by a few different pathologists annually between 2006 and 2020. And primarily, they were interested in Commandra blister rust, stalactiform blister rust, and western galled rust. And they've also been making assessments of tree condition damage and other impacts such as animal damage. So the climate assessments begun in 2007 with the installation of weather stations. Basically, we have a weather station near the center of each of these three trials. Since the trees were planted in 2004, but we didn't get the weather stations in until 2007, we have backdated our weather data back to 2003 to help relate to the disease surveys. And then we also installed microclimate temperature and relative humidity sensors, and that's shown in the bottom right-hand corner, that little white thing on a rebar stake with a GPS on top. Those are little temperature, relative humidity sensors and data loggers in one that were installed close to tree height to represent microsite conditions. And they've been collecting hourly data from 2007 to 2021. The weather stations that we use are onset weather stations where we have wind speed and direction at about 3.5 meters, rain at 3 meters, solar radiation at 3 meters, temperature relative humidity at 2 meters, which is a standard climate variable, leaf wetness at 2 meters, pressure 1.5 meters, and soil moisture and soil temperature at 20 centimeters depth. The climate summaries that we've compiled based on that hourly weather data is first to just do some standard climate summaries. So taking that hourly weather data and making daily mean, maximum, and minimum variables, except for rainfall, which you can only do a daily total for. And then taking that daily data and also converting it to monthly mean, mean maximums and extreme maximums, mean minimums and extreme minimums, as well as creating those same monthly variables into seasonal climate variables. Winter is December to February, spring, March to May, summer, June to August, and fall, September to November, and then annual climate variables as well. And then we've been deriving additional variables, making sure to capture growing season summaries. So growing season we defined as May to September for average temperature, extreme maximum temperature, extreme minimum temperature, mean maximum temperature and mean minimum temperature, total precipitation, and average relative humidity. We've also been calculating growing degree days using a date to accumulation of 200 growing degree day heat units as the start of our growing season, and then calculating a total consecutive growing degree day for each growing season. We're also looking at frosts. So a mild frost being temperatures less than 0, but we also look at a killing potential frost of temperatures less than -5. August minimum temperatures, extreme minimum temperatures, and precipitation are values that Alex Wood deems to be potentially significant for rust conditions in the Bulkley Valley area. And then we've also been calculating potential rust weather wave events, which will be explained on this messy slide here. So wave events come from the published literature of rust development, sporulation, and infection with temperature and relative humidity thresholds. So I've listed a bunch of publications there that have helped us figure out what the state of these potential temperature relative humidity thresholds are known, and then test these based on our field data. So for blister rust wave events where we have hourly temperature and relative humidity, a wave event would be defined as a continuous period of 6 or more hours of temperatures between 10 and 20 degrees and near saturated air, so relative humidity greater or equal to 90%. We can split those rust wave events into different durations. So a short duration is those conditions for 6 to 11 hours. A medium duration is 12 to 23 hours, and a long duration being greater or equal to 24 hours. We don't always have hourly temperature and relative humidity data, so we created a surrogate for that based on daily temperature and precipitation. So I did mention that we had to backdate our weather station data to 2003 in order to relate it to the rust surveys of 2004 at planting. And that meant that we could only have daily temperature and precipitation based on available weather station data that we could backdate for. And so our thresholds for that were to use a daily T-min greater than 10 and Tmax less than 20. And instead of relative humidity, we used precipitation between 1 millimeter and 10 millimeters. 1 millimeter, we justified by saying that would probably mean relative humidity was high, but if precipitation was greater than 10 millimeters, we've sort of assumed that potentially a day with lots of rain or with heavy rain would be not favorable for rust spores, for example, or potentially could wash away any infection conditions. So we had different durations based on when we only had daily data. A short duration event was a daily temperature range of 8.3 to 11.1. A medium was less than 8.3 and a long was less than 8.3 temperature range for 2 or more consecutive days. And that is from the published literature. There's different potential wave event periods. The literature says that potentially July to September is when these wave events could be occurring or when infection is more likely to happen, but we did calculate these wave events from our field data for the entire growing season. We had an inkling that perhaps it isn't confined to July to September based on our field observations. For gall rust wave events, there's different criteria. Temperatures between 5 and 25, so a little bit more generous, and relative humidity greater than or equal to 80% for 24 hours or longer. And the literature says that gall rust wave event period is limited to May to July. So here are some results. We have been testing all of those climate summaries that I had mentioned 2 slides prior, as well as all these different wave event criterias. And we have different criteria and different seasonalities if we're looking at the blister rusts like Commandra and Stalactiform, or if we're looking at gall rust. So it does actually equate to a ton of data that's specific to rust type. And we're still in the exploratory phase. So the surveys were finished in 2020, and I know it's 2025, but we are definitely still exploring this data because it took a good 2 to 3 years to really compile all the data before we could start the analysis. So here's just some of the observations from the Indaco site. The first graph is showing tree condition per year of that survey period. And at the end of the survey period in 2010, unfortunately, about 75% of the trees were dead, primarily from blister rust infections. And that's what's shown in the middle graph there. There's a time series of Commandra, Stalactiform, and gall rust infections. Commandra is red, Stalactiform is yellow, and gall is green. At the Indaco site, Commandra really peaked in 2006, so just a few years after planting, and Stalactiform peaked at about 2008. And then the bottom graph is showing a count of those wave events that I mentioned on the previous slide for each of those years. And here are the same graphs, but for the Thompson site. It's really not that far from the Indaco site, pretty similar conditions. And it did have about 75% of the trees dead by 2020, due mostly again to blister rust infections. So they peaked in about 2006 at the Thompson site. And for Commandra peaked in 2006, Stalactiform peaked in 2007, as did the gall rust. So again, just a few years after planting were the highest percentages of rust infections. And then again, in green, a count of those rust weather wave events. And then the last slide, George, much better survival at the George site, which we're still trying to understand. In terms of the trees that were planted, they were all the same as the Indaco and Thompson sites. So potentially climate or microclimate or these wave events could be a reason why we see lower incidences of rust and higher survival. So just over 40% were dead by the end of the survey period in 2020. And I guess if you're an optimist, that means 60% alive. So that's good. This site is still doing quite well, and we'll continue monitoring it for a number of years to come, I think. Again, in the middle, showing the results of the rust surveys where Camandra has kind of had multiple peaks, as have the other rusts. It's sort of interesting. You know, that to me makes me really want to dig into the climate and microclimate data further to try to see if there's, you know, one particular variable or maybe multiple variables that could be causing those peaks in rust years. So with all those climate summaries I mentioned we have done and those wave events as described in the literature, it's really hard to know which one of those is most important. And we don't really have the statistical power to do a bunch of sophisticated analysis with just the weather station data and looking at average disease levels throughout the whole trials. So one of the things we thought to do was kind of develop a favorable climate condition scorecards, one for blister rust, so Camandra and stalactiform, and then one separate for gall rust, because there are different weather conditions and wave event criteria that are more favorable for gall rusts. So the way we put together these climate condition scorecard was to take only some of those variables we thought were either favorable or unfavorable. Unfavorable would get a negative number. And if the weather variable was one standard deviation from the mean, that would give it a value of +1 or -1, or if it was 2 or more standard deviations from the mean, +2 or -2. And then we summed all of those up, just trying to see if potentially there were years of high rust incidence that would have been associated with maybe multiple climatic factors that would lead to higher levels of diseases in some years compared to others. We're also challenged, and if you're familiar with working with blister rusts, with knowing their developmental period. We're under the assumption that it's the weather conditions of the previous growing season that would have been related to the diseases that were able to be observed in a given year. So we know we have to back up the weather data relationships by at least 1 year, but this actually could be as much as 3 years, and we don't know. And it might not be consistent among years. So it could be a 1-year relationship in 2018, but maybe it was a 3-year developmental period in 2006. We don't know that. So we've been doing a ton of exploratory work with these different developmental periods, trying to look for relationships with wave events and favorable climate conditions. And we're sort of coming up short, but definitely it's still a work in progress. We don't have that issue with gall rust, which is good. The year that the gall rust is observed, we can relate to that growing season's weather data, which is nice. And I'm just showing an example here of gall rust counts on each of the 3 sites of this trial with that favorable climate scorecard. There does seem to be some relationships there, but again, we're still just in the exploratory phase. More analysis is definitely needed. And then lastly on this project, very much interested in figuring out if climate change means that we're going to, well, we are already seeing a higher incidence of rust than we should be, or if we're going to be seeing more in the future. And I think there's probably some good evidence of that when we look at longer term weather station data from the Smithers Airport, for example. We know that frost can be limiting to these rust conditions. And that graph on the left there is showing anomalies of growing season frost days for Smithers. And during most of our field trial, there is much fewer frost days than in the past, which may be why the incidence of rusts have been so high. Also, we've been able to find a statistically significant trend in growing season start date. We've been able to show that the growing season is starting earlier on these sites, and with a longer growing season, I mean, that's good for the growth of the trees, but that also means there's more chances for these rust weather wave events to occur or for favorable climate conditions to occur. So this is still very much a work in progress. We've drafted a technical report on the assessment of this trial, basically the high-level stem rust dynamics in each of the sites and the microclimate conditions. And then we have plans for a technical report number 2, where we will get more into the stem rust dynamics and microclimates using those temperature relative humidity sensors that were installed at tree heights and maybe a little bit more indicative of the rust weather relationships than the weather station in the center of the trials. We are continuing to monitor. We've moved to a 5-year forest health survey, so there will be one happening this year. And the weather stations have continued. One of the interesting things that we've noticed is that even though the graphs kind of show a drop in the last few years of rust, there are new infections occurring on these trees. So we want to make sure to at least go out every year and service the weather stations and have a quick look at how the trees are doing, as well as do those formal forest health surveys every 5 years. So the next project I'll talk about is using weather and microclimate measurements to assess wildfire risk in different stand types. So this is done in collaboration with a grad student from UNBC, Rulan Zio, and his supervisors, Phil Burton and Joseph Shea, as well as Rebecca Ballard has helped with this project as well. So as Dawn mentioned, I'm sure you'll hear more about this in the upcoming seminar series for later this month from Phil. So this is work initiated by Dr. Philip Burton. He was able to get some funds from Natural Resource Canada on a project titled Understanding the Effects of Forest Management and Prior Disturbances on Forest Fire Risk and Behavior. The MSc thesis of Rulan at UNBC is entitled Comparison of Methods to Estimate Fuel Moisture Content in Different Forest Stand Types in Central British Columbia. And then I was brought on to help with Rulan's MSc thesis to bring in that microclimate component. This has partly been funded by the Ministry of Forest Research Program, but also with matching funds from the BC Wildfire Service, looking at just the microclimate and soil effects of these different stand types. So the rationale for this work is to further understand the wildfire skips that were observed in the 2017 and 2018 wildfires in the central interior, where some juvenile forests burned less severely or not at all, whereas older, mature surrounding forests were burned at higher intensity. And this is counter to the understanding that older forests are less susceptible to high intensity wildfires, and it sparked several research projects to investigate. So the sites that I've been involved in and were part of Rulan's master's thesis were 3 sites around the Smithers area. So one is up by Dennis Lake, just on the other side of Hudson Bay Mountain. There's one close to Houston on the Barron Forest Service Road, and then one out by Chapman Lake. And then we have the same design for weather stations in the Prince George area, where we have one west of town in the Bednesty Lake area, one north of town around Stone Creek, and then, sorry, one south of town around Stone Creek and north of town at North Fraser. And then also shown on these maps are the fire weather stations that have also brought in to compare to our own in-stand monitoring. So study design for the weather and microclimate work, as well as the fuel moisture sampling that was done by Roulan, was to find in each of those 6 locations shown on the last site, adjacent, open, mature, and juvenile lodgepole pine stands. So it actually equates to 18 different research installations and areas that were collected for fuel moisture. So the open stands are regenerating clear cuts. They've been planted, so they're very much at the seedling stage. There's still a lot of shrubs and slash. Mature stands are primary old forests that are at least 100 years old, mixed species. They're lower density and patchy. And the juvenile stands are planted lodgepole pine at about 20 to 40 years old. They're pretty dense at about 2 to 3 meters spacing. And all of these stands are subboreal spruce stands. Just one slide on the fuel moisture sampling, because I wasn't involved in this directly, but folks might be curious. This was done the summers of 2021 and 2022, where the student was trying to attempt to match the passing of Landslide 8 and Sentinel-2, because part of his goals were to relate field collected fuel moisture to remotely sensed moisture content. The field collected samples were weighed, dried, and weighed again to calculate their moisture content. And this was done in each of the open, juvenile, and mature stands every few days. So again, a ton of data collected as part of this work. So samples were taken from the duff, so that's forest floor. So primarily the fermentation and humus material beneath any living moss or cover or litter. And his initial results, which have been submitted in his first paper, are that he found higher moisture content in the duff layers in the mature stands compared to the juvenile stands. He also sampled fine woody fuels, so those are dead twigs between 2 to 7 meters in diameter, typically around forest floor, and there was no statistical significance between the mature and juvenile stands. That was the same result also for foliage moisture content, primarily of the conifers. Again, there was no statistical difference in moisture content between the samples taken in the mature stands versus the juvenile stands. But there were, of course, differences with the open stands. And with the remote sensing stuff, I think this is kind of still in the works, but initial results were weak but statistically significant relationships with the field moisture content. So that's promising. A little bit more detail of the microclimate work that I have been doing and have gone beyond the field fuel moisture sampling. And that's, I'm not limited to a 2-year term like a grad student, so I am able to keep these running longer term, and I would like to collect more data to really be able to understand these microclimate and weather differences in these different stand types. So just a little bit about the monitoring design. The open stations all have a full weather station. This is primarily an onset weather station that's solar powered, temperature and relative humidity at 2 meters and at 30 centimeters to understand conditions closer to the ground. We measure surface temperature, wind speed and direction. There's a tipping bucket rain gauge, solar radiation, barometric pressure, soil temperature at 15 centimeters depth, and soil moisture at 5, 15, and 30 centimeters of depth. In the juvenile and mature stands, we try to match as much of those open measurements as possible. So just showing some of the in-stand monitoring and some of the other pictures. That second picture is showing our soil station. So there's a little micro logger that has soil moisture at the 5, 15, and 30 centimeter depths, and then a temperature measurement 30 centimeter above ground, as well as the surface and soil temperature at 15 centimeters. The third picture is showing one of UNBC's weather stations. So 4 of the 6 weather stations in the open are provided by me, but 2 are provided by UNBC. The fourth picture is some more of that in-stand monitoring. We're showing an in-stand tipping bucket rain gauge. That's that white circle with the black top. And then those white things on rebar are temperature relative humidity sensors at 30 centimeters and surface temperature sensors. And then lastly, in-stand wind speed monitoring. Phil Burton and many others agree that potentially differences between these different stand types in wind could be a key variable. There's limitations in monitoring equipment within forest stands, but we're making an effort. So it is really challenging to measure in-stand wind speed, but we have attempted to do so with Davis wind speed and direction sensors. I've taken canopy photos at all of the sites, and here are just examples of what the sky conditions and canopy cover looks like. Obviously, the open stand is open and fully exposed. The juvenile stand is that middle picture, which has lower canopy cover and is pretty densely confined. And then the mature stand on the right, which is pretty shaded, has the greatest canopy cover, but a lot of open patches. And the next few slides, I'll be showing our preliminary data to date on those different weather and microclimate variables between the different stand types, and some of the overall observations to date. So the first graph is showing temperature differences, and this is those 30 centimeter temperature measurements at the 3 different stand types. The graph is showing average temperature, maximum temperature, and minimum temperature. And basically kind of as we would have expected, the mature stands do have the coldest temperatures. The second graph is relative humidity, average relative humidity, maximum and minimum, again in those different graphs between the different stand types, and the mature stands on average are the most humid. When we look at wind speed, it's a bit of a fuzzier picture. For average wind speeds between the different stand types, the mature stands seem to have higher wind speeds than the juvenile stands. However, when we look at maximum wind speed, so potentially during a storm event, the juvenile stands have a higher wind speed than the mature. Looking at rainfall data between the different stand types so far has shown no trends. There's quite a bit of variability in rainfall data and will need to be explored further. Looking at surface temperature on the left of this graph, the differences between surface temperatures and the mature and juvenile sites are variable. Sometimes the mature stand has higher surface temperatures, sometimes it's the juvenile. There's no consistency yet, and this is one of the reasons why I need to continue to monitor. What is interesting to note is the open stands can often have maximum surface temperatures that are well above 30 degrees, whereas that is quite a bit lower in both the juvenile and mature stands. For soil temperature on the right, soil temperature at 15 centimeters depths are nearly consistently coolest in the mature stands compared to the juvenile. Soil moisture has been a challenge. I was really hoping that this would be a key variable for differences between the different stand types, but it's really hard to measure in-stand soil moisture, just having cables on or near the ground and lots of animals and critters, especially in the mature stands where they like to live, chewing on my cables. So we lose a lot of data. We have tried our best to sort of cage up the cables, showed in this picture here, where I've just gotten gutter screens from Home Depot and made my own cages for those cables, which seem to be working thus far, which is fantastic. So hopefully we'll have better soil moisture data in the future. But then the problem with these cages is potentially I'm affecting the infiltration of rainfall to those soil moisture. And that's why they're open, but it still could be having some sort of effect. What we've seen so far is that there's a lot of fluctuation in the open stands with soil moisture, which makes sense, and less so in the juvenile and mature stands. And mature stands had the least fluctuation, so they were never either the wettest nor the driest. With the temperature relative humidity measurements in each of the different stand types, we've been calculating vapor pressure deficit. So vapor pressure deficit is the difference between the amount of moisture in the air and the amount the air could hold when saturated, and can be an indicator of drought or wildfire risk. Just showing a graph on the bottom right there of provincial VPD values, with that peak in 2023 being that dark red graph near the end, the dark red bar near the end of that graph, which related to our worst wildfire season to date for British Columbia. And then the upper graphs are the field data calculated VPDs for different stand types for a couple of these field sites. We've found that the open stands have the highest VPD, which makes sense. And then when we relate between the juvenile and the mature, the picture again is variable. So 4 of the 6 sites VPDs are higher in the juvenile versus the mature, but then for 2 sites, the juvenile VPD is actually less than the mature. So again, I need to do more monitoring. Another thing we've done is try to figure out what might be the peak time of day for wildfire risk based on what's the peak time of day for vapor pressure deficit. Some consistent results between the different sites, and then also in the different stand types. For the site near Houston, we found that this is generally occurring in the open at around 3 o'clock. It would actually be 4 o'clock in daylight time, so in local time. But the juvenile peaks at 1400 PST and the mature at 1300 PST. But then at one of our sites closer to Prince George, it was nearly consistently around 1400 PST. And then the last slide of data from this field trial is we're calculating our own fire weather indices based on our field data using the Canadian Forest Fire Weather System. So things like fine field moisture code, duff moisture code, drought code, buildup index, initial spread index, and fire weather indices have all been calculated for each of the seasons we've been collecting data to date. And then we compare that to nearby BC Wildfire Service weather stations that are also calculating those codes. There's been some good consistency between what we're calculating at our sites and the BC Wildfire Service data. The differences being we are able to use our microclimate data to know when snow has left these sites and then start our fire weather codes as soon as the snow is gone. Which is the goal of the BC Wildfire Service, but obviously they can't be everywhere all the time. And so sometimes these are turned on before that occurs or maybe later, and that really can affect how these codes are calculated. So for this project, we still have to get more data, do some statistical analysis, compare the weather data with the fuel moisture data a little bit more thoroughly, and then also compare with remote sensing data. And then the data for this project has also been useful to BC Wildfire Service and Canadian Forest Service to improving their spring startup codes with instant data. And I'll just wrap it up here. So hopefully you kind of got from that is I've been collecting a ton of data for a variety of different projects and was only able to highlight two in the Skeena region today. But if you're interested in any of the data or any of the other projects, please feel free to shoot me an email. Check out that website of weather station data. And there's also a ton of other opportunities if you were interested in any of this data for some of your own research, just showing how it might be neat to use some of this data to look at tree growth. And that picture on the left where there's quite excellent lodgepole pine growth. And then there's sites where we're not monitoring rust, but we have these instant temperature relative humidity sensors and rust, which you might be able to pick out from the orange at the bottom of that lodgepole pine tree. And I'll leave it there for questions. Thank you so much.